Okay, seems to be everybody. Okay, so let's start the second day of APLAS, and we start with an invited talk by Albert Cohen from Google Research France. So if you look at the list of his publication, you can see he published in compiler constructions, in code generation optimizations, ACM transactions on architecture and code optimizations. So he looks like a low-level backend compiler guy. Well, and it is not wrong. I mean, no, he certainly works in the area both of programming languages, well, compiler constructions, and system, because that's what he compiles, I mean, for what the architecture compiles for. But there is more than meets the eye. So although definitely it's true that Albert is worried about cache misses and branch mispredictions and page faults, but he also worries that, well, the code that we generate, or the compiler generates, that it isn't just a blob that we dump into the file and forget about. The code has some structure, some constraints, some, for example, at the very least, that the code should be well-formed and well-typed, and hopefully it has some other properties. And if we are mindful of those properties and maybe hopefully expose them to the program or to the user, then, well, first of all, we can assure that we, don't generate nonsense. And second, maybe we can have a queue to more interesting optimizations and more assured optimizations. And that's what probably the area, that's what motivated Albert and his long work on polyhedral loop transformations. Well, nowadays it's used pervasively in high-performance computing. It's actually part of LLVM, and maybe GCC as well. I mean, they got it. And recently, he's been involved in MLIR, which is a kind of higher level of LLVM, and it's about to be, or maybe has become already a part of LLVM. It's actually part of the LLVM repository, so it's kind of officially part of LLVM. And that's what hopefully he will tell about it.
I might disappoint you, but you'll see. Thank you, Oleg, for the kind introduction. Yes, it has been a long journey from the back end to higher levels up and down again. So I'm going to try to give you a little bit of a motivation for doing even more of this, but by far, I'm not going to cover all the topics you covered and you described, and in particular, MLIR will be very short. So, okay, so it's great to be here. Thank you for your kind invitation. So I used to work in academia for a long time at INRIA, and I joined Google about 6 years ago. And indeed, one of the main projects we initiated was this MLIR, higher level abstraction for constructing compilers. But I won't say too much. So I had as much fun writing the title as working on the slides themselves, so hopefully you get some of the jokes here. I don't know anything about K-pop or J-pop or anything, but yeah, compilation and pop and whatnot, so that sounded interesting. So and then kernels, yes, I didn't know before, but actually when you do popcorn, the source you're compiling into popcorn is actually called a kernel. And we want to pop them, obviously that's much better. So I'm going to tell you stories about popping kernels. Yeah, so one of the problems with high-level programming is that actually practitioners like high-level languages that have not found so much success in practice, like people writing very high-performance numerical libraries, for example, for CPU, GPUs, accelerators. They tend to write low-level kernel code. It's called a kernel. Actually, machine learning people hate it because kernels means something completely different in statistics. But that's what people do. They end up writing a lot of low-level code. So we seem to have completely failed because we have been claiming for decades in academia and also in industry that we should write high-level code. It has so much benefits, even for low-level like tricks, optimizations, and stuff. And so I know many of you here work on staging, for example, or partial evaluation, or all these techniques have been very successful at eliminating performance penalty, for example, from high-level languages. But still, people write kernels. So how come? By the way, when I say kernel, this is just like a brief overview, but for example, on GPU today, the popular kernel programming languages, so they are languages, they are a little bbit higher level than assembly and stuff, but they are not much higher level. They have a little bit of software engineering flavor to it. So you don't have to write like CUDA, C, C++ directly. You can write Python code that looks very much like what the machine wants to see. So maybe you heard about Triton. For GPUs, there are other like C++ layers with lots of ugly template metaprogramming. Sorry for those fans of C++ here. I think there are not so many, but anyway, it's kind of staging. It's called Cycle and Cutlass from NVIDIA. And there are a little bit better formed DSLs, but still low-level ones, like PALAS, you may not have heard about. It's part of the JAX ML framework, and it lets you generate code not only for GPUs, but also for Google TPUs. And you have similar approaches from AMD, and maybe you heard about the Mojo language from Modular, which has been based on MLIR as well. And there are many other proposals from academia, of course. More broadly, yeah, that's what practitioners see. I mean, they get experience with high-level languages, they get burnt, doesn't do what they want, so they have to essentially forget about them and forgo all the abstractions they love, or maybe not, but anyway, they go low level. So one thing to mention is not only about performance tricks, it's also about some expressiveness limitations. So most of the high-level languages, they come with, let's say, a contract with the programmer that you have to use like higher-order combinators like map, reduce, this type of things to get good performance automatically from the compiler. And sometimes, of course, using these abstractions comes with some expressiveness limitations. Think of like sparse tensors, you have arrays that have irregular shapes, etc. Those may not be natively supported by your abstractions. So it's not only performance tricks. So who is the culprit for all of this? Who is actually what is the reason, or who, I don't know, I guess what still, for having low-level code all over the place? Maybe some of you have seen this picture. I just removed the title, but this is Gemini. So this is Google's ChatGPT, if you may. So this is our foundation model that gets derived into many instances for many different purposes. So it's much more than ChatGPT. It's actually all the models that we derive for different types of applications, from Gmail to chatbots, to image generation, etc., all the way down to your phone on the right, and maybe higher level data center scale generative models on the left. So this is why I'm sitting, and not actually standing here in front of you, is that we have very big problems right now in terms of how to run those complex models fast with low energy footprint, on limited memory if it's on the phone, etc., etc. And there is basically no limit to how much performance people would like to optimize in those applications. So that's the reason, and it's actually a pretty big problem, as you can imagine. So all the predictions we made, not only Google, but all the hyperscalers made predictions about cutting our carbon footprint and not only predictions, also strong commitments by 2027, 2030, depending, etc., on the company. In the last couple of years, it has been very hard. Actually, it's not only because of ML, there are many other reasons, but it's very hard to meet the demand of those applications without using a lot of energy. So there are many ways to mitigate that. There are lots of controversies as well. So not only, I mean, more technical things as well, like on the right. This controversial paper in the Communications of ACM about whether it's better energy-wise to run on the cloud or on phones or whatnot. I'm not entering that debate, but it's a big problem, of course. We need to do that, so that's why people are not ready to pay the price of high-level abstractions at no cost at all. I mean, it's just too costly, actually. So the problem is even bigger than that. So this is just like a nice business slide about how much Google has invested into ML-based solutions over more than 20 years already. And most of these nice images correspond to a lot of interesting different like diversity of models and scales over the years running in different applications. Basically, every Google services have to some degree, they depend on ML at this point. So that's good news actually for us, because as programming language people and compiler people, we are interested in having many programs to compile, not just one. If it was just like one model of one version of Gemini, probably it's actually fine to write it at low level because you end up spending much more time writing the compiler for it otherwise. So, but it's good news that we have many applications to compile, at least for now. And okay, I started saying that people write kernels, but actually we did claim for a long time that we solved that problem. That basically because of that reason of having so many programs to compile, we did invest for, I guess, 70 years in performance portability. Not just portability, but Fortran was very much motivated already in the late 50s with performance portability in mind. So didn't we solve that problem? I mean, actually, we did make a lot of progress. On CPU, most people now write, for example, Rust code these days that is memory safe with a little bit of effort to get both memory safety and performance, but you do get performance in Rust. You don't have to write assembly, and most of your code is actually safe. Okay? So we did succeed on CPU, but what about like the most numerically intensive kernels? What about hardware accelerators like GPUs, etc.? There is still a lot of work to go. Sometimes it works, sometimes it doesn't. And most importantly, in this current race for generative AI, not soon enough. Like programmers really want, like domain experts really want performance yesterday, not waiting a few more months before the compiler gets there. So almost 1 year ago, actually, I gave a presentation with another hopefully funny title at ETH Zurich, which was about, so I tried to translate it to Japanese, but I didn't check, so hopefully this is more or less what it means. It has to do with rabbits and hunting them and basically getting none of them if you try to run 2 rabbits at once. That's what I got. But in English, it translates into having your cake and eating it too, and in French, it's called avoir le beurre et l'argent du beurre. So it's related to butter. So it's all cultural, but it's the same idea. So performance engineers, they want that. They want a compiler, and they want it now to deliver the best performance. But we know that writing a compiler takes time, and that's the connection with MLIR. So a lot of the challenge here is having the right software infrastructure, having the right abstractions to build the compiler itself. So Seok-Young mentioned lots of meta-level software engineering yesterday. I mean, it's all about constructing the compiler faster to deliver much better results so that you don't have to wait until 5 p.m. to get your cake. Right, so that was I'm not going to go through that presentation again, but it's also recorded if you're interested. So just zooming out a bit, what people care about in ML, I'm not talking only about ML, but that's the driving force for this work, is what they call high-level embedded domain-specific languages for machine learning. So JAX is the one that got developed at Google, so it's open source. It's embedded into Python because that's the dominating language for ML, and it does have a lot of merit in terms of like symbolic reasoning and staging and reflection and all kinds of things. You can do both nasty things and good things with it. JAX in particular is purely functional, and it has this great ability to compose functions, pure functions on tensors, which are also values, with so-called transformations. And there is actually interesting research to be done in that space. I'll say more about this, but the great thing with JAX is you can write numerical code. In this case, it's just like one layer of a perceptron running on a higher order tensor, and a loss function that computes whether you're far or not from the ground truth when training a neural network. I'm not going through the math, but you recognize your typical perceptron code functions if you're familiar with Python syntax. The great thing is that you can take this loss function, compute the gradient of it. You can JIT compile the result. This is a piece of abstract code that you can compile. You can also distribute it automatically, VMAP, that's what it will do. You can run it, for example, on the GPU or multiple GPUs, even multiple machines, by just annotating this VMAP with some like mesh annotation saying how the data is going to be distributed over these different machines and devices. So it's very nice because you don't change anything to your source code, you just compose transformations. Of course, underneath, there are a lot of challenges. First of all, how do you get these transformations to compose? So here there is interesting research. For example, those of you interested in staging, and I'm one of them, I'm not so happy with the ability to transform the code. I would rather stage the computation directly and have more type safety built in the framework. So that's not guaranteed right now, but it happens to be type safe in practice, but it's a lot of effort. It's not given by construction in the embedded DSL, so there's interesting research to be done there. And what I'm focusing on today is what happens below. In fact, most of JAX magic happens not in JAX itself. It's a tracing compiler, it does all kinds of nice things, but it happens underneath, and it's called XLA, which is a domain-specific compiler, code generator and compiler for linear algebra. So XLA came in originally for TPUs. That was actually the only way to program Google TPUs back in the days, like 2014, 15. And now it also has backends for diverse GPUs and CPUs. And XLA is indeed taking care of all the abstraction penalty removal. When you say hyperbolic tangent, or when you say square of metric product of tensors, etc., this is all mapped into so-called compute graphs of XLA. So what is an XLA compute graph? So XLA is a great representative of domain-specific languages that have success in HPC. It's basically what most machine models look like from a high level. So like 99% of the code in a machine learning model is about composing these pure functions on tensors or streams of tensors that apply essentially linear algebra operations. So some of the operations are not plain linear algebra. You can even get sorting and stuff like that, but in most of the cases, it's linear algebra, and typically dense and rectangular, at least at the high level. So that's great. I mean, domain-specific languages have been successful in HPC. This is one example, mostly because the abstractions map the demand, and because, of course, the compiler can do good stuff with it. So what type of good stuff? And that's really performance portability I was talking about. So it's a JIT compiler, so it does it fast first, which is significant. So you don't have to go through XLA every time you run a model in JAX. I didn't mention the others like PyTorch, TensorFlow, etc., but it's all the same story. It has to compile if you want to optimize, but you don't have to. You can also run the code like one kernel at a time. It's portable, and it eliminates all kinds of overheads. For example, dispatch overhead when you communicate between the host and the GPU or the TPU. That's, of course, very slow. Memory bandwidth limitations, etc. So you also don't want round trip to memory. So that's what Loop Fusion is for in Oleg mentioned polyhedral compilers, so same kind of story here. You have a lot of fusion going on to avoid round trips to memory and tiling or blocking for cache misses, etc. On GPUs, it may not be caches, it's more like software managed memories. Same thing for accelerators. All of this is taken care of automatically in the compiler. You don't have to think about it. And lots of lower level backend stuff as well. So this is great, it works. Most people have used XLA with good success. Actually, so great that people, including ourselves and colleagues from ETH Zurich, have been also working on raising abstractions from, let's say, loops in C, for example, all the way up to those type of compute graphs automatically, just to compare with parallelizing compilers or handwritten numerical libraries. And we got reasonable success. That was one of the initial illustrations of the MLIR project, actually, showing that you can take low-level LLVM code, I mean intermediate representation coming from Clang, from C, and raising it, or C++, even templates as well, raising it automatically to higher-level numerical, like linear algebra code and, abstractions, and lowering down, again, using the domain-specific techniques. When you're lucky enough, that raising process works. So we had this nice picture here of having a lift that raises you automatically, and not for free, but without effort, to the top of the mountain, and then you ride the slope down. This is thanks to our Swiss friends. So this kind of works, but actually not really. I told you, people still write kernels. So why? I mean, all of this looks like we have good solutions. So this is an interesting picture I generated using some earlier version of our image generation generative AI. So it has a few issues there. I would not write that gondola. First of all, it goes downhill, so it's not really useful. And second, if you look carefully, actually it's holding to the cable through one of the protective gear devices, not actually from the center of the gondola. So it's, wow, I don't know actually how these things work. So it's kind of crazy. So I would say that's basically how performance engineers see domain-specific languages. Yes, in most cases, like from the distance, it looks great, and actually you can make good use of it, but in fact, it also hallucinates, like in this picture. So they don't trust compiler optimizations. We can say everything we want about removing abstraction penalty, unless you're an expert in the compiler itself. Typically, at some point, you'll be hit by some like unexpected behavior, and it's very hard to understand what's going on. I mean, this is really a hard scientific problem. I think it's how to not only provide best effort solutions, but also trustworthy solutions that even non-experts in the technology they are using can actually use it. I mean, it's called Apple, I think, in the world. But so if you have a nice interface to technology that you have no clue about how it works, and you can fully depend on it, actually it's more like safety critical systems like planes and stuff. That's what we aim for. We want to have this, and unfortunately DSLs for HPC, they are not so much trustworthy at this point, because they do the best they can, but not always succeed. So still we have nice theories and practice behind to get there, to get good performance, trust in a robust way. For example, if you just want to optimize matrix product, there is, I don't know how many millions of papers on the topics and a lot of methodology as well. The kind of dominating framework is called BLISS from the University of Texas, and his first name I think is Katsuhige, I'm not sure how to pronounce, Goto, actually from Japan originally, and they had this BLISS framework methodology published that is now implemented in essentially every numerical library, whether you're compiling to like wafer scale engine like the Cerebras CS chip, or a very tiny edge device like the Google's Edge TPU. This is always the same story. You have this recursive decomposition into multiple levels of tiles. Every tile level corresponds to some level of memory hierarchy, or some level where parallelism gets expressed on the machine, all the way down to registers and some form of vector computing topology at the very bottom with some custom instructions. So this decomposition, this recursive decomposition is very familiar. Of course, it depends on the machine, depends on the size of the matrices, etc. But it's very, very systematic. So we could say, okay, this is not such a hard problem to automate how to write this. And indeed, there are good results if you only look at matrix product, at kind of nicely shaped problems like powers of 2, and I mean, in general, you can do a good job automatically on matrix product, but it's not the whole story. That's why we are here. We are doing programming languages because we are not only programming matrix product, as I mentioned earlier. For example, we are programming transformers, but hopefully not only transformers. So what are transformers? So the T of ChatGPT, maybe some of you don't know this, means transformers, which was a paper published by Googlers like 7 years ago, which has nice properties in terms of combining so-called attention mechanisms, so being able to statistically focus the information on parts of a sequence of tokens, can be text, can be the decomposition of an image, or all kinds of media information, and the ability to train reasonably easily. So it's not, I mean, when you do ML, you have always this tension between expressiveness, so capturing a lot of either kind of direct linear operations or more indirect capabilities, and the ability to more abstract capabilities, and the ability to train, to learn automatically. It's not only piling up layers of abstraction and layers of blocks of all kinds of numerical code, but you also have to make it differentiable, and the whole thing has to converge when you train. So this is basically one of these great successes of transformers, being able to do that. And the core mathematical object is called attention, as I mentioned. And it's, okay, 3 matrix product, compute these 3 matrices Q, K, and V, which has some relation with key value stores or databases, if you want, but in a soft, like differentiable way. And then another matrix product with a transpose matrix and some additional vector operations, including exponentials and divisions. Okay, it's not very fancy, numerically speaking, but it's not matrix product. It's matrix product plus a few other things that have to be taken care of. And if you want to go from these nice mathematical results running on small problems to millions of tokens, to do whatever all the time for millions of clients. For example, what Gemini offers at Google, long context means that you have a lot of tokens. That's actually a big challenge. So it's both an algorithmic challenge and a performance engineering challenge, and that's why we are here. So, for example, one of the challenges is parallelism. And so far, I only mentioned code generation as a challenge, like going down to like caches and vectors, etc. But of course, higher up, you also have to scale to multiple threads, multiple GPUs, etc. And this is one example of, it's actually chronologically, these are all the dimensions of parallelism that have been used in machine learning for inference. Of course, training has used parallelism for a long time, but even for inference only, this is what you need today to run some of the larger models. Like, for example, GLAM was one of the first mixture of experts model. It needs, like the model size can be like hundreds of billion values or more. So you need not only like batch, like independent problems to be run in parallel, you also need to exploit parallelism within the model, you need to pipeline, you need to parallelize within the tensors themselves, also distribute across multiple devices, etc. So that's really a large problem, and all dimensions of parallelism have to be exploited. And parallelism is not an easy beast. Okay, concurrency is already hard enough, but parallelism, like on real machines, you have to deal with data center networks, you have to deal with finer grain communication between devices. All of these have different capabilities like bandwidth, latencies, memory buffers to hide those latencies, a lot of lower level performance considerations to take care of. And this is just a high level overview. There is actually a nice blog post at the bottom if you're interested on kind of surveying all the types of networks we use at Google, including optical, etc. And this is very hard to model. So if I told you this nice matrix product story, yes, we kind of know how to do it, but if you factor in all this complexity with parallelism and communications, like explicit communications, things become really tricky. So last but not least, I'm not trying to depress you completely, but I'm trying to give you real evidence for why kernels are still around. One last thing is that it's not only parallelism, it's also algorithmic. So if you want to, or I would say kind of algebraic, more precise. If you want to get good performance with attention, it's not only matrix products, because it's multiple matrix products, and in the middle there are some other operations like softmax, which is a sum of exponential essentially. And to get those operations, to make them efficient, you have to fuse, as I mentioned at the beginning. And to fuse, it gets tricky when you have these interesting operations in the middle, like sums of exponentials, because typically these are not linear operations. But they are kind of morphisms still, as you know, like exponential is a morphism from the addition to the multiplication on real numbers. And that's, maybe you heard about flash attention in the space of optimizing neural networks. It's all about that. It's actually optimizing attention by observing some of the morphism properties that operate underneath. And instead of having two matrix products communicating through the main memory of your device, you can actually tile those matrix products and fuse at the tile level. But then you have to do a few tricks of renormalization across those sums of exponentials. Essentially, you don't have the full sum, so you have to compute partial sums. Those have to be divided and remultiplied every now and then, because you kind of partially accumulate those partial sums. This is nice algebra stuff that fits on a couple of lines of LaTeX. But, okay, you have to do it. And that's absolutely key to get good performance. In particular, that's key to save memory so that you can fuse the computation. And unfortunately, this is typically not done automatically by the compiler. Actually, we did it at Google even before the flash attention paper was published. We had a similar technique on TPUs that kind of did the work, not optimally, but it was already a good start. But if you look at the state-of-the-art flash attention-like optimizations, all these fusions and tricks with exponential being a morphism, they are typically implemented at low level in CUDA, or those DSLs I mentioned, like Triton, or for TPUs also PALAS in the JAX framework. So, okay, that's kind of a good reason. Okay, you see on the right, the performance benefits of doing this can be huge because you're saving so much on memory transfers. Okay, so now let's step back a little bit. So we have seen performance portability being a challenge. We had some success, like XLA is a great success, and still people write low-level kernels. So basically, we have to live with it at this point. That's what I hopefully convinced you about. So there are interesting programming language challenges associated with designing this whole stack, from the transformations in JAX all the way down to these backend considerations. But whatever you do on the compiler space, performance engineers will never be happy because it's not robust enough and because it takes too much time. They don't want to wait for your compiler to be ready. They need it now. Okay? And yet another reason, which is a little bit more, let's say, society-oriented or economic, I don't know, is that, that's why we are regressing in the end, is that you do get personal interest in not using the compiler because you're doing it yourself. Like when you're an engineer in a company and you are coding, you get some results. Oh, I get this speed up myself. So that's good for you. You get promoted, etc. So why would you wait for the compiler team to do it if you can do it yourself and get all the credit? I didn't say that. So we have to live with kernels for all kinds of good reasons. I mentioned also like sparse, right, all kinds of irregular computations. So you have expressiveness limitations. I mean, it's not easy to think of everything in advance. Really, you cannot. So kernels have to be around for some time. So what can we do? Either we just say, okay, fine, these are two different worlds. I don't care. In academia, you can always do that. I mean, you can say, I want to play with that particular problem, and please do. I mean, we have to solve every single problem. But, okay, I'm not satisfied with that. We have to find some kind of ways to reconcile people doing kernel programming, like hardcore performance engineers, and people writing compilers for the long term. And that was this, like, having your cake at 5 p.m. idea. I mean, making sure we can do both, having the cake and eating it as well. So there have been lots of techniques proposed to do that. I mentioned staging. More generally, people have been doing reflective programming. So JAX is a good example of like transformations embedded in the DSL. You can do that directly in the language itself or on the better, actually more controllable, more domesticated on some abstract syntax trees that get built from a DSL. And for example, you may have heard of schedule language like Halide, TVM, and a lot of more academic ones as well. Those have like two sides. One algorithmic side, I'll say more about it, but I won't have much time. And one like transformation script, essentially, that explains how to optimize the algorithm and to map it on the target. So we have this combination of transformation scripts, composition of transformations with numerical algorithms. So those are all interesting approaches to do kind of domesticated reflection. Staging is even better, but more restricted in terms of practicality. And so I had the privilege to write a paper with Oleg like ages ago on how to use staging to build a code generator basically for HPC at the time. So we are still there. I mean, we have not made much progress, except at that case, at that time, we were trying to make it type safe. And okay, this is still a problem. Everything I mentioned until now is not type safe. So if you can do like type safe staging for JAX, for XLA, that would be great. Please let me know. I'm interested in collaborating. This is still an open problem. I'm not going to define staging here. I think everyone knows about it. I think there is also an interest in, I would say, more software engineering approaches to building DSLs. So I mentioned two great projects, one called Build It from MIT. The student is actually looking for a job, I think, by the way. And another earlier work from University of Saarbrücken in Germany. So these are great approaches to design, let's say, compiler construction frameworks. So there is, of course, there is a programming language aspect, but there is also a lot of software engineering to it. And these have been inspiration for the latter, and kind of design at the same time for the former, for MLIR itself. So what are good abstractions for building reflective techniques that are safe and domain-specific support? So beyond reflection and staging, there has been a lot of work on machine learning. Maybe I should have started saying that the first answer to, compilers are not good enough is, use ML. I mean, that means humans are not good enough at writing compilers, but that doesn't mean compilers cannot do it. You just need better heuristics. And it's not completely absurd. I mean, that's actually for a very long time, even before 2006, I had some work in the area. Like most of the works have to do with heuristics, like trying to fine-tune heuristics that humans came up with. For example, improving inlining or improving register allocation, etc., using like fine-tuning the weights of the heuristics is something that's already in production in LLVM. And Google actually had a lot of investments on that. So you can do a lot of so-called auto-tuning, meaning you generate code, you try, you measure performance, you try to learn some kind of general properties of the behavior of your heuristic, and you fine-tune the heuristic by learning on the large-scale corpus of programs. So this is great, so this was compiled by students from IIT Hyderabad I'm collaborating with, and actually we do try to push that to the next level. So not only fine-tuning heuristics that humans came up with, but also learning heuristics from scratch. And one nice approach for doing that is reinforcement learning. So you can actually see your compiler more like some kind of agent that tries to navigate a space of correct transformations. Hopefully, in the case of compilers, you do care about correctness, and profitable ones. So like a game, so there are actually game theoretic foundations for that, but I'm not at all an expert. It's like a single-player game, so there is no opponent in general. You can see the machine as an opponent, but I'm not sure it helps. And you try to navigate that space of, for example, in this case, register allocation constraints, like interference rules, whatever instruction set architecture restrictions you have on register usage. And you have to take some decisions. For example, you have to, of course, no way to explain that picture here, but you have to split live ranges, you have to color registers, and then, oh, you change your mind, actually, I should rather do that, so you uncolor the register, and then you find a way to spill it to the stack and whatnot. So those are all decisions you can iteratively take. So it's fun, it's actually successful. You can get more or less the same results as the best heuristics that are currently implemented in LLVM for free. I mean, not for free, you need to train on large machines, but without much human intervention. Of course, it's very slow. I mean, all this interaction goes through Python and RPC calls across the compiler and the machine learning framework. I mean, this is very inefficient, but it works, okay? And talking about efficiency, the next piece of work we did together with other colleagues at Google is try to make it actually more practical. So how to build compiler infrastructures so that you can interact more easily with machine learning frameworks. So I had this another nice title, but I won't explain it, about how we can systematically compile with ML in the loop of the compiler. And there are many ways to do it, depending on whether you do research, whether you are training, whether you're interested in deploying in production. For example, when you compile your favorite Linux distribution from scratch, you don't want to wait for ages for whatever ML framework to also compile. So you need all kinds of software engineering tricks as well to make it transparent. So many of these questions have been discussed in this in that paper. So I think this is getting mature now, not only heuristics, fine-tuning heuristics, but also learning from scratch, using ML techniques to really help accelerate building compilers. But it's not enough, of course. I'm just saying this is one part of the problem. I'm giving you hints for more research. I'm not solving the problems here. I mentioned scheduling languages earlier, like TVM, and the most popular one is Elide, which is used in every phone that you have for nice image processing, among other things. So actually, this is a great success, mostly because domain experts come in two flavors. There are the domain experts who know the math, and there are domain experts who know how to optimize the math. So that gives them two different languages, one for the people who know the math, and one for the people who want to play the tricks to get the math to run fast. And that's what the schedule language is about. So for example, we worked on this tensor comprehension language for ML when I was collaborating with Facebook at the time. And there has been a lot of work at NVIDIA, etc. as well. This is actually time-tested. So the oldest ID along those lines I heard about were from the early 90s, both from the group of Bill Pugh at Maryland and in Rennes at INRIA, also in France, in the case of a domain-specific language for high-level synthesis called Alpha, which is a nice functional language, by the way, functional array language. And we did also some work, so just before collaborating with Oleg, actually, I was doing that as well, with a scripting language called Urg. At the time, nobody knew what it meant, but now it's obvious. So the schedules are great, but they are not necessarily what people like in HPC. So in HPC, people write code like OpenMP and stuff. Okay, pragmas. I won't say more, but sometimes you want those schedules to be embedded into the code, so you can do it. You can use pragmas. We also published on that. I'm not going to spend much time on this. It's not, I would say it's not like in opposition, it's more like a complementary. And then maybe the last bit of insights is you can also let the compiler collaborate with performance engineers in more implicit ways. For example, you can make the compiler aware of the semantics of kernels, of highly optimized code, in this case, numerical libraries. So maybe you heard about telescoping languages, some work from Ken Kennedy's group, also 20 years ago, where the idea is to semantically annotate more like static analysis to scale to like interprocedural modular levels. You may want to do that for code generation as well. So you have annotations attached with library functions that tell you how to further apply transformations downstream inside the library itself. So it's not like a frozen library anymore. It's more like you tell the recipe for opening the box of library calls, and then you can, like, for example, fuse across library calls. You can vectorize them internally, etc. So that was pretty nice. That favors reuse and composition at a higher level of abstraction, not just like an ABI where you're calling a function. You're actually staging the call basically into some intermediate representation that will let you apply those transformations. So this is great. Similar to that, we worked also some time back on the concept of split compiler, split compilers, meaning that some heuristics, now it's not the IR itself, it's not the semantics, it's more like heuristic information can be also propagated downstream. So you know at high level, for example, that some, the first paper at the top was about register allocation. So you can make register allocators much better if you pre-compute a priority of spilling registers, which is actually the most costly, the most really NP-complete part of register allocation. And then only on the back end, when you know exactly how many registers you have and how many live variables you have, you can take the decisions of spilling the registers. But you don't have to do that at the same level. You can kind of anticipate at high level, and you have more static information at that time than when you actually take the decisions downstream. So that this has been applied to vectorization and other approaches as well. So similar to telescoping languages here. So I think these ideas are still very interesting in the case of collaborating with kernels as well. Okay, maybe just one thing, just to contradict Oleg. Compilers have to be safe, and type safety, etc. is great. Actually, in the field of domain-specific high-performance languages, you can kind of revisit that idea. I mean, I hate it myself, but think of those domain-specific languages a little bit like scripting languages, like shell scripts, etc. So sometimes you write a shell script, or maybe you use Python, or I don't know, or no code, just for one task. Like you want to sort your vacation pictures, or rename the files or whatnot. So you just write a script with a regular expression. Like the next day you forgot what it is about, you're going to drop that code. So you don't care if it's correct. I mean, usually you have some kind of file system that lets you backtrack in case you didn't do the right thing. So the code doesn't really have to be correct. And a lot of synthesis techniques, they do that. They try, and they revert in case the code is not correct. So you may need a verification, like translation validation techniques, for example, to do that. But in general, you don't really care about correctness right away. You may care about correctness at a later stage. So that, I think, is also something we have to keep in mind when writing compilers for performance engineers, is like many of the performance engineering tasks have nothing to do with correctness. They have to do with intuition of this is what the machine wants to see, so let me rewrite the program in a way that's going to be fast, and then later on, okay, they do spend some time actually making the program do the right thing. But the first task is actually figuring out what the machine wants to see. And so that's, I think the tools should also see the problem that way. It's like focusing first on performance in that case, and then later on, okay, eventually let's fix the code to do the right thing, but still following a schema that's well suitable for performance. And there are a lot of methodologies for doing that, but I don't have time. Finally, something about MLIR. So I've covered a range of techniques from staging all the way to split, like telescoping languages, etc. So we have designed a framework now already 5 years ago that we announced in 2019. There was a nice blog post that was tweeted by the big boss, which was great. It's a collaboration with many companies. Actually, the good news is not MLIR is not a Google product at all. It's completely part of LLVM. The code has been transferred to the LLVM Foundation, and most of the contributions actually are not from Google. So that's a great success in that sense. So we are using it, of course, but it's really a community project, and it's primarily a software engineering project. So it's not about building a semantics-rich framework. You can do your own type systems. You can do all kinds of fancy, nice PR stuff on top of it, but in itself, it's mostly LLVM-style infrastructure for doing it. Okay, it's in C++, so you may not like it, but it's reasonably fast and efficient. But importantly, it has layering on top that lets you do almost everything you can do in C++ in Python. And there have been people playing with Haskell as well, and Rust, because there is a C binding interface. And so all of this, now the ecosystem is actually largely contributed by people doing only Python compiler construction on top of MLIR, for example. I mentioned a couple of projects later. I don't have time to explain you what this is in detail, but it has SSA. Actually, we realized that SSA with phi functions from the late 80s was great for like backend languages, but if you work at higher levels with nesting of structures, maybe actually continuation passing style with functions, and in this case block arguments may be better than free functions. So interesting debate that gets revisited. No time to get into that. So what we do with MLIR in particular, and I cannot go into details, but we just published a paper on the topic. Sorry, this is not LCPC 2005. This is CGO 2025. We didn't publish like 20 years ago on MLIR. So one great thing we can do with MLIR is we can use the intermediate representation, which is serializable. It is like LLVM. It has text as a programming language. In this case, a meta-programming language for transformations. So if you want to write your own compiler passes, or if you want to write custom scripts, as I was mentioning earlier, maybe just like single-use scripts or more durable things, you can do it in the IR itself. Most of the time, you don't even have to write any code. You can use pattern matching for that. You can use some conditional execution of the patterns, etc., all in the so-called transform dialect. And again, this is in development, so you can look into it. It's great. There is a tutorial about it by my colleagues, but it's transformational. So if you want something that's staged, probably you can still work on it. There is still room for a lot of research, and it's not type safe in any way. So but that's one thing that people like. I don't have time to go into details, but I'll share the slides. You have a Python interface for it, so you can build your own passes. You can do auto-tuning with it. You can do all kinds of separation from transformations, from policy. For example, if you want to do ML applied to an MLIR compiler, you can build the transformations capabilities on one side, and you can do auto-tuning on the other. And finally, you can write your own compiler passes, as I mentioned, by just chaining some transformations that are expressed directly in the IR itself. So it's really meta-programming technique for building, for example, you can even build new passes on the fly, dynamically load them, etc. So until now, none of this was possible. And in particular, if you want to apply this to different types of abstractions that can be represented in MLIR as dialects, you can also do it dynamically. You can like load a new abstraction that you care about, or I invented this new sparse representation for a tensor. I want operations on those. Let me write a compiler pass to optimize those abstractions. You can do that on the fly. You don't even have to recompile the compiler. So let's get back to the original problem. We do want performance portability. We want a long-term investment in the compiler, and we want also to use it right away, so not waiting for it to bake. So where did we get with all of the information I throw at you? So that was part of that earlier presentation last year. So I started at the time saying, yeah, maybe it's all about ML. Yeah, it's true that the reason I'm here is ML. We have people paying for all of this. But ML may not solve all your problems. We can use ML in compilers, it's great, but it's not going to solve all your problems. It's about domain-specific compilers. Yes, of course, like JAX, for example, XLA, these are great successes of domain-specific languages and frameworks that get good performance, but it's not enough. It's not enough to get good performance all the time in a robust way and fast enough. So people are getting hungry. This is all about compiler construction. Yes, you can use MLIR. There is great software engineering progress. There is probably more work to be done on safety and more semantically sound techniques, but it's not enough still. We do want our cake at this point. So one solution, and I will finish with that, is there is probably one way to get the job done, which is in academia in particular, when the problem is too hard, okay, you move to the next problem, an even more complex one, even more difficult one, and then you can publish more on the topic. So that's also what we are doing. So if the problem of performance portability with kernels is not enough, you can try to make it, something I didn't know that existed, but it may be too difficult to pop the kernels, so you can half pop the kernels. I didn't know that existed, but I found, I have no clue if it tastes any good. But you can try it, for example, to ask your compiler to, that's kind of the best way to collaborate with performance engineers, is to say, on demand, let the compiler do what it does well, and maybe some parts of the code you still want to write by hand. So I'm going to skip the details of this, but generally the idea is to retire any form of low-level coding. You have to stage everything, and you have to let the compiler decide at the last minute which version of the code you want to use. So you kind of delay the instantiation of low-level code, but you don't completely leave it up. I mean, you have to leave the option for the performance engineer to do all kinds of tricks, but you want kind of to delay the need for that as much as possible, and not think of it as a last-minute hack, like a custom call or library call on the side. You have to build your compiler for integrating the ability to make this low-level code available from the start. So I'm skipping the techniques to do that. We did some work, early work in that direction. Time is out, so no cake yet. Sorry, I'm not providing you any food. No popcorn. So any kernels left behind? Unfortunately, yes. We have to live with it. We have to play with kernels because programmers, some of them, do care about performance for good reasons. And I think that the optimistic message is that I gave you a wide range of reasons to be optimistic. Compilers can still help. We should find a way to collaborate more deeply with performance engineers. Can be with schedules, can be with better software engineering, can be providing them with more safety. And of course, making machine learning part of the picture is important as well, because all of this automation, any automation we can get is important. Thank you.
Okay, so thank you for all the different ways you're trying to attack this problem. I apologize for the negativity, but I don't quite see this like solving the problem you described at the beginning, like people writing kernels by hand. But there are technologies that they use, that they consistently use, something like macros, for instance, or even in Boost you see like really sick template programming, meta-programming. And they seem to be okay with adopting those things. What do you think is the difference between those things that get consistently adopted versus the academic efforts that don't?
So that's a great question. So I think I kind of answered that by saying, yes, this is the way to go. We have to do that. The main problem is not so much the technology, is what is the problem you want to solve with it. So I think those staged approach, the ones that have been successful in practice, have been very pragmatic. They have been solving a programming problem. They have not been solving an optimization problem. For example, staging in like template metaprogramming for numerical libraries like Eigen in C++, or there are better libraries for, more abstract approaches to this. They just try to help one programmer, or maybe a handful of programmers who wanted to get more productivity in writing low-level vector code with intrinsics, or assembly code. And so they did it for themselves. They have their own code generator, and they realized that staging was helpful to get more reuse, etc. If you use staging to build a compiler to do things automatically behind your back, you're solving a bit more difficult problem with the same technique. So it's not the technique, the problem is really what you try to solve. So what I'm pushing for solving the harder problem, which is using those techniques that have been successful, but to kind of build compilers alongside code generation frameworks that are more specific, so that the two can be reconciled. So if you use staging for building your compiler, hopefully you can reuse some of the compiler code inside the domain-specific, like application-specific code, and vice versa. That's what this half-popped kernels vision is about. I'm not solving the problem. I'm giving you some directions. You may like it or not, but really it's not the technology which is the adoption challenge here. It's the problem you're solving with the technology.
All right, thank you.
Great talk. So for traditional compiler writers, there was Spec 2000, where you don't need to know the workloads of everyone. You just run the benchmark and you gain some %. Here, the kind of targets you have in mind is there also a standard benchmark of what kind of baseline we can improve, or because it feels like it's a lot of data. It's a very complicated, you need a data center to benchmark that the thing worked, right? Did improve
So for benchmarking itself, yes, it's a difficult problem, yes. So for benchmarking, you may not need that much resources. For training, yes, if you use ML techniques, you do need a lot of trial and error process. But the benchmarking problem, it depends if you're interested in covering a large range of problems, or if you just care about your own like very specific model. Like if you're optimizing transformers for one particular version of Gemini, you know exactly the shapes of every linear algebra operation. All the sizes are known, etc. So you can focus on just like one particular benchmark and fine tune on this. You need only a handful of machines for doing that. Yes, it can be iterative, it can be kind of brute force, but it doesn't require like a huge amount of infrastructure. If you want to train a compiler to do this systematically in every possible library function, for example, that you care about, or fusion of all possible combinatorial explosion of things, yes, then that becomes interesting. No, but there is no like systematic benchmark suite for training, let's say. For evaluation, I would say yes.
Okay. So it's been a long-held view of mine that optimization is for not thinking about performance, and when you want to extract actual performance, you really want to be precise and have control and all that. Mm-hmm. And this half-popped kernel story of yours seems to go in that direction, but generally you seem to be of the opinion that even for very high performance code, where you care about performance, when you think about performance, then optimizations are still important, very important, extremely important. Like, can you, it's a philosophical question here, but like, where do you stand on this? Like, correct me if my long-held view is wrong.
Yeah, I'm not sure I got the beginning. So
the beginning.
Yeah, of your.
I was saying that like compiler optimization is for not thinking about performance.
Oh, not thinking. That's what I meant.
Yeah.
Okay. Yeah. So I think that will never be reconciled. So you have the optimization for the common case and the optimization for the specific case, and those are different objectives. So, like for example, most of computer architecture courses, like 101 course by Yale Pat at UT Austin, started by let's optimize for the common case. I mean, it's like it comes directly from whatever universal forces have been around. So that's not true anymore. Like most of computer architecture today, it's not about building the next x86 processor. It's building domain-specific accelerators. So it's really a different optimization objective. So performance engineers, they care about the specific one. Compilers, they used to care more about the common case. So I think we have to reconcile the two by saying, if you work on your specific case for long enough, it will become some kind of common case. So these are different objectives, but let's find a common ground. That's where I stand. That's why it's half-popped. You have to find a way to decide whether you want to stick with your specialization at the extreme, meaning that you cannot reuse any of these around, or at least not at the level you'd like, or whether you can actually reuse some components that have been designed for the common case. But that reuse cannot be just optimization heuristics. It has to be lower-level abstractions that compose in a way that will solve your problem. MLIR is about that. So it's more like meta-level in the sense that you have semantic building blocks you can assemble. You can reuse code in particular to solve your problem, but it's not just about tweaking heuristics. That's not enough. These heuristics are solving a different common case problem.
So ultimately what this could look like is that you have optimizations as kind of primitives that you can call. You can say this code is optimized that way. Like you decide which part of the compiler works on your code.
Yeah, exactly. So I mean, if you do kind of progressive refinement as your architecture for your compiler, you can say you have different levels of abstractions and you're lowering abstractions one after another. Some of them may actually join the entry point, or you could call them escape hatches for low-level programmers willing to intervene. So if you have different ways of reaching that level of abstraction, either domain-specific language or maybe like just a diversion through some kind of custom technique that goes back into the main compiler flow, as soon as you have this progressive refinement chain, I think you can do that. That's my philosophical answer. But there's software engineering to back it up. Like essentially MLIR is there for you. Yeah, all the OptiML. Yeah.
Had expose some part of the compiler to the user, so the user can write a program and use the compiler. Say, okay, optimize this part of type check, this part. I just generated a new rearranged expression, retype check it, and give the type.
Yeah.
So it's kind of, but it turns out, it's actually very hard, and also very hard to compile, and also makes compiler very, very slow.
Yeah. So it's called Scala is called Python these days,
yeah,
but that's what they do.
Turns out to be, yes, it's a good thing for one, but from the point of view of compiler, many users actually not a good thing. So there is a big tension in here, big challenge how to actually expose part of the compiler and still, have a good performance in the compiler.
I agree.
And also, not break the compiler.
I agree. That was not a question, but I agree.